Hey everyone, welcome back to 197 Concepts. In this video, I'm going to discuss with you the procedure or the program that is used to make the UART possible. Okay, so our main topic today is UART. So UART is nothing but Universal Asynchronous Receiver and Transmitter. Okay, so by using this protocol, it's a standard protocol that is used between two electronic devices in order to make them communicate with each other. So for today, what we are going to do is we are going to take an microcontroller, which is our 8051 standard microcontroller, and we are getting a serial display or serial terminal and a microcontroller. Then we are making the data exchange between these two with a baud rate of 9600. Then half of 9600 is, I believe, it's 4800, and then at 2400. Okay, so these are the baud rates. So these are the baud rates, and on these rates we are going to make a communication between 8051 and our serial terminal. Okay, so for that, what I'm going to do is I'm going to use the Keil MicroVision for the programming part, and I'm going to use the Proteus for the simulation purpose. Okay, so in order to show you the transmission of data between our microcontroller and serial terminal, I'm going to use Proteus. For the programming, I'm going to use the Keil MicroVision. Okay, so before entering into the programming section, there are some basic things that we have to know before starting of the program. The very first thing that you might have uh, got a doubt is nothing but the word baud rate. Okay, it's the baud rate. The very first thing that we have to know is the baud rate. Okay, so baud rate is a very new word for you, and if you don't know, of course, if you don't know, so baud rate is nothing but the number of times a signal is changing its state. Okay, the number of times a signal is changing its state. Okay, so for example, imagine that my signal is starting at logic 0. So this is logic 0, and after the initially starting it, it's changing to logic 1. This is logic 1, this is logic 0. So this is one baud rate, this is one baud rate. Then immediately this L1 is dropping to L0. Okay, so it's dropping to L0, then this is baud rate 2. Again, it's going to shift to L1, so this is baud rate 3. Okay, if it again falls to 0, logic 0, then it's baud rate 4, and so on. The cycle continues. Okay, so basically the idea is if my signal transitions its position, it's not like it should be in order. So it was L1, and it should drop back to L0. Only then we count the cycle. Or it was initially it was L0, now it is L1. Only the up transitions, only the logic ones will be counted. It's not like that. So whatever the signal is at the position, if it is changing its state, then it is counted as baud rate. Okay, so that way we are having these three baud rates. Another baud rate is the double of 96,000. I believe not 9600. It's like 11,200 or 600. I'm not sure about it, but the commonly used baud rate is 9600. And for a slower communication, we use 4800, and even for a slower communication, we use 2400. Right now, for our basic purpose, everyone is using the 9600 baud rate. Okay, now, so that means for every second there will be 9600 transitions in the clock signal of the microcontroller. So that is the meaning. Similarly, if it is 4800, that means there will be 4800 transitions per second in the clock signal. So half of 4800 is again 2400. So there will be 2400 logic ones and 2400 logic zeros. So that is the meaning of this 4800. In the same way, 9600 means you have 4800 L1s, logic ones, and in the same way, you have 4800 of logic zeros. So that's our baud rate. Okay, now that's the main thing, and keep in mind this is going to be useful for us. And the next most important thing is we should know some basic formula, as we are going to use timers for this experiment or for this usage. So the very first formula that I'm going to write is, of course, our timer frequency, which is nothing but just let me change the color, or else let us go to the other page. So after knowing all the basic concepts, that is our baud rates and whatever software we are using. So our next thing is we should know some basic calculations that are used for configuring the timers. So you might be familiar that our experiment is based on communication, and we are trying to carry out the universal serial communication, not serial, asynchronous communication. Yeah, you can call it a serial also, but there is no handshake here. So that's why we call this as asynchronous receiver and transmitter. Okay, so UART. For that, we should know some basic formulae, and these formulas are basically there are. Similar, these formulas are basically similar with the formulae that we used in timer calculations also. So if you want those formulae, you can check the video. I will leave the link in the description box. And there are some changes here. I said similar, but not 100% similar. So there are some changes. So let us just check out those formulae. So the very first thing that we have to check out, or the first formula that we have to keep in mind is the uh, timer frequency. Okay, so the very first formula is timer frequency. So even this formula will also be available in our timers while configuring in our timers video also. So when you are configuring the timers, you will get this formula also, but there is a small catch here. So it is f oscillator, so frequency of oscillator divided by 12 multiplied by 32. Okay, so this 12 I have carried out, so it's the same formula. So there we used to have, okay, I will just change the pen. So I will take it yellow color. So there we used to have f oscillator divided by 12. So there I have explained why we have used this 12 and all. Okay, so just go and check out that video if you want to. But here we have an addition of 32. Okay, so this 32 is related with UART communication. Okay, so this 32 is related to UART communication. And if I get into this 32, it's a very huge topic that becomes another video. So for time being, let us stick to the value 32, or else it will be 16. Okay, na? So it's only two values, either 32 or 16. So this is based upon the configuration of your timer. So SMOD register. So if your SMOD register is loaded with the value of 0, then we use the value 32. And if our SMOD register is triggered or loaded with the value 1, then we use the value 16. Okay, so what's the difference means, if you get the lower number, 32 is a higher number and 16 is a lower number. So if you get the number lower, then definitely your speed of communication or the speed of data exchange will increase. So it's vice versa. So keep in mind we are using 32 into denominator. So that's why if you divide our oscillator frequency with 16, it definitely our speed, the communication speed is going to increase. Okay, so that's the main thing we have to consider. And then the next formula. So that's our basic formula, and our next formula is timer tick period. So even this formula was also available there. So we have used this formula, and just like there, what we have done, we have just reversed this timer frequency formula. Here, what we are going to do is we are just going to reverse this timer frequency formula. That means 12 multiplied by 32 whole divided by f oscillator. So it's the same formula. Okay, now our third formula is our third formula is count. Okay, so this count is going to change a little bit here. So there we use the required time delay and the timer tick period. So here also what we are going to calculate is, of course, we are going to use our required time delay. Yeah, let's write it in the full form. Required time delay divided by timer tick period. Okay, so it's the same one. And finally, the fourth one is also the same, which is nothing but our preload value. So this is the very simplest one, preload value, and this is nothing but our maximum value or maximum, what we call it as, count. Okay, so yeah, let's go with value, max value minus count. Okay, so this is the easiest one, and this is the only thing which has not changed here. Other than that, all the three formula, in all the three formulae, we have a change when we are dealing with registers and when we are dealing with communication, serial communication. Okay, so yeah, that's the thing. And let us do the calculations one by one. Okay, so let me just erase these ink strokes. So the one that I've used here, or else, yeah, I will erase this also. I will rewrite the formula. So that's uh, F oscillator divided by 12 multiplied by 32. Okay, so that's our basic formula. Now let us do the calculation. Okay, so when we come to our calculation, the very first thing is we have to know our timer frequency. To know our timer frequency, what we are going to do is timer frequency is equals to, so generally our 8051, the microcontroller 8051 is going to operate and on 11.0492 megahertz of frequency. So this is the standard frequency. Okay, so multiply divided by 12 into 32. So what I'm going to do is, instead of taking this 11.0492 that gives some decimal values, instead of that, what I am going to do is I'm going to consider this as 12 megahertz. So this will make the calculation much easier. It will give an approximate value. So if you go in this manner also, if you consider the 11.0492 megahertz of frequency at the end point, at the, what we say, the last formula, the preload value, there you're going to do some approximations. Okay, so yeah, I will tell there when I come there. Okay, so 12 megahertz divided by 12 multiplied by 32. So this will give me 1 by 32 of megahertz. So if we calculate 1 by 32 of megahertz, let me just open the calculator. We won't be needing any squares here, so no need of scientific. We can just go for the standard one. So yeah, it's 1 bit divided by 32. So 1 divided by 32, that will give me a 0.03125. So 0.03125. So that will be, yeah, 0.03125 of megahertz. Okay. Now, when you convert this megahertz, this is 10 to the power of 6. So 0.03125 multiplied by 10 to the power of 6. So yeah, this will give me 1, 2, 3. Yeah, 1, 2, 3, 4, 5, 6. Okay. So that's 31,250 hertz. Okay. So instead, just for the simplification of calculations, I have converted this mega into a real value. Instead of keeping all those megas and all the units, you get confused, like 10 to the power of 6 multiplied by 10 to the power of minus 3 and all and all. So instead of that, just do this. This will be much better. And then the timer tick, if you continue this one, this will be 12 multiplied by 32. Okay, whole divided by, mm, keep this value. No, that's same color. Record this value, and then so 12 multiplied by 32 divided by 12 megahertz. So this again, so 12 is going to be cancel out, and then I will be having 32 divided by mega. When this comes up, it becomes micro. So it's multiplied by 10 to the power of minus 6. Hence, we get at the final time, the final value will be 32 microseconds. Okay, so this is the second value you have to keep in mind. Okay, so this is the second value that we need. Okay, then here when we come to the count, there is another calculation that you have to know. Is brown visible? No, brown is not at all visible on this, and that's an ink pen. We cannot take that. Let me change the color of this. Yeah, let's go with the pink. I think pink is visible, but not much. What other colors do I have? Okay, I will go with white. There's no other choice. Okay, so yes, when you come for the count, the formula is required time played divided by total, timer tick period. So timer tick period is 32 microseconds, but we don't know the required time delay. We only know the baud rate. Okay, so the baud rate, so the baud rate is 9600. That means our signal is going to shift 9600 times in a second. Okay, that we know, but we don't know what is the bit duration. So, what time it takes for our signal. So, what time it takes for our signal to make 9600 changes. So, yeah, that is a bit troublesome here. So, for that, what we have to do is for getting the required time delay, we have another formula. For that, we have RTD, required time delay is equals to, that means required time delay is nothing but our bit duration, which is given by the formula 1 divided by targeted baud rate. Okay, so that means we know our baud rate is 9600, that means 9600. So just the inverse of 9600 will give me our bit duration or our required time delay. So if you open the calculator again, yeah, here what we have, 1 divided by 9600. So that's a huge value. It's in exponential. Let us see in scientific ones. So 1 divided by 9600. So it's getting in, yeah, it's going in exponential. Instead of that, what I'm going to do is 1 divided by 96. What's the value? It's 0 point. So what I'm going to do is I'm going to write this as 1 by 96 multiplied by 100. So that will give me the value 0 0.01041. So yeah, that will give me the value 0.01041. Again, I have divided by 100. Okay, so in order to make it in micros, or in order to get the value, so see, if I get more zeros, if I again divide it with 0, what I'm going to get is 0.0, yeah, 012, 1041. Okay, so if you multiply this with 100, we get 0 0. So yeah, there should be one more 0 here. I just forward it. 0 0 1041. Now if you multiply with this 100, so 1 2, that will be again, no, that's problematic. Okay, 1041. Now, if you multiply this with 100, you get 0, 1 dot here and 1 dot here. That's 0.01041. That's our value, right, in our calculator. Yeah, 0.01041. 0.01041. Okay. Now, in order to make this in micros, what I'm going to do is I'm going to multiply this value with 10 to the power of 4 and sorry, micro, right? So to 10 to the power of 6 divided by 10 to the power of 6. Now, if I multiply this with 6, what is going to happen is 1, 2, 3, 4, 5, 6. So that's 104.1 multiplied by 10 to the power of minus 6. That is 104.1 microseconds. Okay, so that's our required time delay. So that is our required time delay for a baud rate of 9600. So that's it. And when you come for the count, so now our main calculation is going to start. So when you come for the count, what is going to happen is you are going to substitute this value. So 104.1 microseconds. So that is equals to uh, 104.1 micro is 10 to the power of minus 6 divided by. So timer tick rate, that is 32 microseconds. So this is again 10 to the power of minus 6. So these two gets cancelled. Now what we have to do is we have to divide 104.1, that is decimal 1, multiply divided by 32. So 104.1 divided by 32. So I get 3.25. So 3.25. Okay, so this is our count. Okay, so this is our count. Now what we are going to do is finally we need the preload value. So here when you come to this formula, you have to know what timer you are using and what mode you are using. For example, I will be using the timer one. Definitely everyone, whoever is trying to do the communication, whoever is trying to do the serial communication, must and should use the timer one itself. So timer 0 is restricted for internal delays or internal errors, or what we say, interrupts, internal maskable and non-maskable interrupts. For that, we will be using timer 0. Of course, we do have some other functions also, but basically, when it comes for serial communications or any kind of communication, the timer 0 will be fixed for interrupts itself. Only timer 1 will be available. So in which mode? That's our choice. So it can be mode 0, mode 1, mode 2, or mode 3. What I'm going to do is I'm going to use this timer in mode 2 because I need the communication to be carried out continuously in a repetition manner. So that's why mode 2 is nothing but our 8-bit auto reload mode. So 8-bit auto reload mode, automatic mode. So in a short manner, what I'm going to write it is 8-bit automatic mode. Okay. So to know what is this mode, uh, I will discuss that in another video because we have to do it in detail, or else try to check our timer. Try to check my timers video. I might have discussed about those while discussing timers. A brief discussion might have been given there, description or definitions or whatever it is. It might be I might have defined there. Just check that check those videos once. Okay. So yeah, when you come here in 8-bit mode, the maximum value is 2 power 8, which is equals to 2 power 256. 2 power 8 is equals to 256. So 256 is not our maximum value. So 255 is our maximum value as we are going to count from 0 to 255. So total we get a value of 256, but the maximum value is 255. So 255 minus 3. But what the value we have got here is when you do the count value, you have got 3.25, right? 3.25. This is rounded up. Okay. So this has been adjusted, and 255 minus 3 is nothing but our 252. Okay. So our value is 252. Okay. Now you might ask me why we have reduced this 3.25 into 3. because this count value is nothing but our logical bits that we are going to load in our timer. So 252 is the value of our logical bit. So in our computing world, in our electronic world, there is no such bit of 3.25. So there are 3 bits. Okay, so there is no 3 1/4 bits or 3.5 bit, 3 of a bit. It's not like that. Either there are 3 bits, or either there are 4 bits, or either there are 2 bits. Okay, so it is in the terms of integers itself. It is not in the terms of float. Okay, so the value is always an integer. Hence, what we are going to do is we are going to reduce this 3.25a as 3. Okay, so that's a basic formula that you have to know. And now the very most important thing that you have to consider is the loading of this value, the loading of 252 into the timer value. Okay, now keep in mind this 252. What I'm going to do is I'm going to write a total of 8 bits starting from 1. So 1, 2, no, I will change the color, just a minute, so that it will be much easier for us. Let us go with sky blue. So yeah, not 0, it's 1, 2, 4, 8. Then we have 16, 32, 64, and 128. Okay, now what I have to do is what I have to do is yeah, I have to write this again. Okay, so these are our 8 bits. So as I'm using timer 1 in mode 2, so this it has a maximum value of a maximum number of 8 bits. So I have taken 8 bits. Now what I have to do is I have to write a value, or I have to decide a binary combination whose total weightage will be equals to 252. Okay, so for that, definitely I need 124, hence this will be logic 1. Okay, so 124 plus 64. I will do the split screen here. So yeah, when you come here, so 124 plus 64. When you do this, it doesn't slide there. Definitely. Yeah. So now 124 plus 64 will give you a total of 188, which is less than our 252. Hence, what I need is I need the value 64 also. I need the value 64 also. Then in this 64, if I add 32 also, then it's 220. Definitely it's less than 252. Hence, it is also a logic 1. Plus 16. So plus 16 will give me 236. So 236. Okay. So all four logic ones, then still 236 is less than 252. Hence, I'm going to add another weight, that is 8. So that will give me a value of 244. Now 244 plus 4, it will be 248. So 248, then 248, 250. Oh, this is 128. This is not 124, that's 128. So yeah, we have to do the calculation again. Okay, We have to do this calculation again. Okay, you might have understood now. I will go a little bit quicker now. 128 plus 64 plus 32 plus 16. So the total value is 240. So it's definitely less than 252. So in the first set of 4 bits, I definitely need all 4 logic ones. Now, when I add 8, so that's 248 plus 4. Okay, that's 252. So that's it. I'm going to add 1100. Okay, now here, when you combine all these 4 bits, okay, in order to convert this into hexadecimal, when you take when you combine all these 4 bits, that means these 4 bits, you get the character F, and when you combine all these, you get a value of 12. So 12 is represented by the value, I believe. So yeah, 0 is for A, and P, yeah, that's 10, 11, and 12. That's C. Okay, so FC. Okay, so what we are going to load the value is 0xFC in the timer register. I believe that's not the right value. Let me just check it once. So I did a small mistake here. So what I told you is, while calculating the count value, we are going to count so 255. So instead of 255, it's a total value. So including 0, we get a value of 256, right? So 256. So 256 minus 3, that is 250, 253 instead of 252. So that's why what we get is 1101. Okay, so 8 plus 4, 12, 12 plus 1, 13. So 13 is represented by the number D. That's why we are going to load our timer register with 0xFD. Okay, now if you check the program, so that's the whole calculations and all. Now, if you check the program, the very first thing that we are going to do here is, of course, we are initializing all the registers with 0. Okay, we are registering all the we are loading all the registers with 0 value, and we are making a long jump to start, then origin, and then start. Okay, we are loading some value 30H. Now, first of all, we are configuring our TMOD. We are configuring our timers. So I need timer 1 in mode 2, so 8-bit auto reload. So I'm going to use timer 1 in mode 2. That's why the TMOD has to be loaded with the value 20H. So 20H, when you write this in a hexadecimal form or in the binary form, so you get 0010 and 0000. So if you verify the TMOD register bits individually, it will tell that you are initializing the timer 1 in mode 2. Okay, then next TH1 0FD. So what we are doing is, we are loading the higher byte of timer 1 with 0FDH. So 0FDH is nothing but our value 253. Okay, and then we are configuring our SCON register with 50H. So that's mode 1 8-bit UART, and then we are enabling the receiver pin. And finally, we are initiating the transmission process, and we are doing a loop here that tells us to transmit the character A. Okay, that tells us to transmit the character A on a repeated process. So you cannot transfer this directly. You just have to move this into accumulator, and then the accumulator is going to transmit the data for us. Okay, so that's the whole thing. And here is our transmit loop. So a call transmit, we are calling this loop, and again we are jumping into the main loop. That means here we are jumping back to this section. And what this transmit is going to do is, it's going to load the value that is present in accumulator register into the serial buffer register, and then it is telling us to wait for some time before jumping. Okay, jump unless and until you don't get a 0. Okay, so which is definitely not true in our case, as we are sending some data. So that's why it's a continuous process. And then finally, we are telling it to clear the trap flag of timer return, and then end the program. Okay, so that's the whole program. And let us try this in the Keil. But before going to that, I just need to share with you small information. So this whole process is for finding out or configuring our serial communication with a baud rate of 9600. So this whole process is same when you go for the baud rate of 4800 or when you go with the baud rate of 2400. This whole process, that means the finding of the baud rate, the calculations and all this process, this every process is similar. The only difference that you get is finding out the count value. Okay, so finding of this count value, because here required time delay will be our targeted baud rate, that is 1 divided by 2400 or 1 divided by 4800. You get a respective value, and that respective value will tell us our count. So you will be load that values here, and then you get the specific preload values. Okay, so that's the only difference. And based on the preload value that you get here, you are going to change this 0 fd or else whatever value you are having. Okay, so it's the same process, no need to worry, just do the little bit of calculations and change only that value. You don't have to change all the settings of timers and all. Okay, so yeah, very quickly what I'm going to do is I'm just going to open the Keil because I have to show you once. So I'm opening this Keil MicroVision software now. And here I'm just going in the project, new MicroVision project. And on the desktop, I'm creating a folder called as UART communication. Okay. So yes, my project name will be UART com. So done. Here I'm going to search for 89C51 atmel 89C51. Click on OK. I don't need the startup files. So yeah, that's it. Okay. So source group. What I need to do here is I need to add a new item. Okay. So here I'm going to use ASM file and it's UART com communication, shortcut for communication. Here, what I'm going to do is simply I'm just going to paste our program. Yeah, it's in Notepad also. That's a calculator. Yeah, I've pasted my program and I'm going to save it and then build the target. So no errors. So for example, if I just forget to type this enter and enter this, click on build target, then definitely I will get some warnings here. So missing end statement. So that's why what we are going to do is we are going to type this, and so it's a case insensitive language. Whatever you type, there is no effect based on the sensitive, based on the case of your typing. So it will take smaller case and capital case, no problem, and that's it. So no errors here. What I'm going to do is I'm going to convert this into an hex file. For that, simply just click on right click on source group, and then options for source group one. So yeah, not this one, target one, options for target one. Here, what we do is we go into the output tab, and then we click on create hex file. One more thing that we have to observe here is in the target, your XTEL megahertz. So XTEL is your crystal oscillator frequency. So here it's 24 megahertz. It should be 12 because we have done all the calculation assuming that our microprocessor, our microcontroller 8051 is working on 12 megahertz. To be more specific, you can type 11.0492 megahertz also, but for approximation value, what I'm going to do is I'm just going to type 12 megahertz. Okay, so click on OK, and we have also checked the value to create hex file. Okay, so click it on OK, and one more time, click on the build target. So target has been built and our hex file is also created. Now what we have to do is we have to open Proteus. So Proteus, where is it? So that I can create a new project. New project. Yeah, I'm selecting the path here. Desktop, UART communication, select folder, and UART. Just click on next, finish. No changes. The only thing that I have to select here is 89C51. That's it. And definitely a virtual terminal. 89C51. So here what I have to do is I have to just make the connections across. So in that way they can, so when this sends the message, this can receive, and when this sends the message, this can receive. So yeah, I need to load the program values. So objects, UART hex, okay, and the baud rate, it's 9600. So no problem. If you have 2400 or 48, you have to be mindful here. You have to change the baud rate. So if it is 48, simply type 4800, or if you're doing a 2400, just do 2400. So I'm going with 9600. We have done all the calculations based on this. I'm just keeping that and just running this simulation. So I did get some thing here, character, but it's not repeating. So just let me change the value here to 11.0492, and now let us try. Yeah, I did get the correct character, but it's not going in a repetition manner. So for that, what we have to do is we have to go here, target, right click on it, and options, and the frequency should be 11.0492. So click on OK. Just build the target once again. Of course, we do need the hex file. So just go on Proteus here and just run this. Now, see, we did get the character. It's not going with the loop. Maybe it takes time. It takes time. So overall, you did get the character here. Okay. So because it's a timer and all those functions have to keep on rotating. It has to complete itself, and then it has to go back into the loop. So that is taking time, but the whole procedure is the same thing. Okay. So this was the output that I got when I tried the previous experiment. So it might be the problem of frequency itself, but you can tell this way that our communication is being established. So 11.0492 megahertz. Just let me recheck this. What is the operating frequency of 8051? 11.0592. Okay. So 11.0592 megahertz, and here also again build the target, come back here. Okay, now let me run this. No, we are getting only a single character, so there might be some logical error, but yes, you did get the character here, so that's the main thing. and it might be a logical error or frequency mismatch or whatever, or the clock frequency mismatch also you cannot say that. You have to just debug it. Okay, so I hope you have understood our communication establishment here, the establishing of communication between 8051 and any other. So here we have just connected a virtual terminal in order to get the output. So that is establishing the UART communication with 8051. Hope you have understood the experiment. That's it for this video, and see you in the next video. Thank you.